Hello everyone. I welcome all of you to the 45th session of the course Energy Law. In today's session, we will explore on the topic Energy Security in a Changing World. Let us quickly recap what we have covered in the previous session. In the previous session, we examined energy transition, technology and security. We started our discussion with an examination of renewables and new vulnerabilities. Then we discussed critical mineral security, digitalization and cyber security, and climate change and energy resilience. Then we discussed a few selected case studies. Today we turn to some of the most frontier developments in global energy security, those occurring above the earth, on the oceans, and in the rapidly changing polar regions. These spaces are becoming the next strategic theaters of energy innovation, geopolitical rivalry, and regulatory uncertainty. We start our discussion with an understanding on space-based and offshore energy systems. Then we will move on to climate tipping points and non-linear risk, strategic foresight and global futures for energy security, quantum technologies and energy security, and then finally, space weather and solar storm risk. Let us briefly examine the background of our discussion. Energy security is no longer confined to terrestrial resources and conventional vulnerabilities, but is shaped by technological leaps and planetary scale risk. Traditional frameworks focused on oil shocks, supply chains, and geopolitics. But the world we are entering involves orbital solar power platforms, quantum cyber threats, energy systems vulnerable to solar storms, non-linear climate tipping points, and strategic foresight tools to anticipate crisis scenarios. This session brings together these cutting-edge dimensions to expand our understanding of what energy security means in a rapidly transforming world. Let us examine space-based and offshore energy systems. Space-based solar power, or SBSP, is a concept that has been around since 1960s. The idea is very simple. Instead of placing solar panels on Earth, we deploy massive solar collectors in orbit where sunlight is constant and uninterrupted. These satellites then convert solar energy into microwaves or laser beams and transmit the power to receiving stations on Earth. You may think of it as taking the idea of solar farms and moving them outside the atmosphere where there are no clouds, no nights, and no weather disruptions. Advantages include continuous 24/7 solar exposure, no intermittency unlike terrestrial solar, enormous theoretical capacity as orbit can host solar arrays of almost any scale, minimal land footprint. The ground infrastructure is limited to a receiving station. and long-term decarbonization potential, as SBSP is a stable, ultra-large renewable source. If successful, SBSP could significantly reshape global energy hierarchies, favoring states with advanced launch capabilities, orbital manufacturing capacity, and satellite maintenance technology. However, space-based solar power also introduces profound security uncertainties. For instance, interference with satellites. Orbital power platforms increase congestion in already crowded orbital pathways, heightening collision, jamming, and debris risk. Beam misalignment. Even slight deviation of a microwave or laser beam could have operational or safety consequences on Earth. And dual use concerns. A high energy transformation beam could theoretically be exploited for military purposes, raising weaponization anxieties. Now we move from space to the oceans, another rapidly evolving energy frontier. Modern offshore energy systems now include floating wind farms, subsea hydrogen production units, deep ocean electricity cables, and floating solar platforms. These infrastructures expand energy capacity but also extend vulnerability into difficult to police maritime zones. Key vulnerabilities include sabotage and hybrid attacks, maritime piracy and interference, jurisdictional ambiguity, and climate threats. Finally, we turn to the Arctic, one of the world's fastest changing regions. As ice melts due to climate change, new LNG shipping routes like the Northern Sea Route are becoming seasonally viable. This creates attractive, shorter paths between Europe and Asia. Let us examine climate tipping points and non-linear risk. In traditional energy planning, we often assume the world behaves in a predictable linear way. Temperatures rise gradually, demand increases steadily, and infrastructure stresses can be anticipated. But modern climate science shows this is no longer true. We now face tipping points, moments where the climate system can shift suddenly and irreversibly, with enormous implications for energy security. Let us begin with the breakdown of large climate systems that have remained stable for thousands of years. The Atlantic meridional overturning circulation, an ocean conveyor belt slows or collapses. Europe could face extreme cold spells. Wind patterns may weaken, reducing wind power output. And hydropower yields could decline due to altered precipitation. This is not a distant threat. Early signs of AMOC weakening are already being observed. India's monsoon governs coal transport, hydropower generation, and agricultural energy use. Increasing variability means Coal supply chains get disrupted by floods or heat. Hydro reservoirs fluctuate unpredictably. And agricultural energy demand spikes during drought years. In short, climate instability directly destabilizes the energy system. Let us examine compound and cascading events. Examples include heat waves that can result in soaring electricity demand, transmission line sag, and ultimately grid collapse. Drought, it can result in hydropower shortages, expensive thermal generation, and therefore utilities enter financial stress. And wildfires, which can burn transmission corridors, create regional blackout, and ultimately water pumping and health systems will fail. These are called black sky events, multi-day system-wide disruptions that exceed our traditional N1 contingency planning. In such events, recovery is slow, expensive, and socially destabilizing. Let us examine renewables and moving climate baselines. Renewables depend directly on climate patterns, but as baselines shift, the resource potential itself changes. For example, wind regimes in many regions are projected to weaken or shift by 2040. The security concerns include stranded solar assets, insurance retreat from high-risk zones. Solar, hydro, and bioenergy face similar risk, making climate adaptive renewable planning essential. Let us examine energy climate migration pressures. As climate impacts intensify, millions may be displaced. This creates two major pressures: urban energy stress, as unplanned population inflow increases electricity and fuel demand. Border and regional instability, as states may compete over water, food, and energy resources. These pressures transform climate change from an environmental issue into a strategic energy security challenge. Let us examine strategic foresight and global futures for energy security. In today's world, energy security is no longer about reacting to a crisis. It is about anticipating them before they happen. Strategic foresight provides the tools to understand long-term trends, emerging risks, and future technological disruptions. We begin with horizon scanning, which is the continuous monitoring of weak signals that may indicate future disruptions. Modern tools allow this to happen in real time. AI-based geopolitical analytics help detect early signs of conflict, sanctions, political instability, or resource nationalism. Satellite-based early warning systems monitor droughts, storms, crop failures, and water stress, events that can destabilize energy production and supply chain. Supply chain monitoring platforms track bottlenecks in LNG, battery minerals, transformers, and solar components. Rare earth catalyzation indicators help detect coordinated market manipulation by producing states. Strategic foresight goes further than monitoring. It prepares for multiple future possibilities through scenario planning. We use scenario sets such as a world with persistent El Nino, causing chronic droughts and heat waves, a cyber-induced national blackout, testing digital resilience, military confrontation in the Arctic, affecting LNG and shipping routes, and the geopolitical consequences of global oil demand peaking, reshaping alliances and revenue flows. Once scenarios are developed, they are tested through wargaming, which examines institutional readiness. Can agencies respond quickly? Civil-military coordination. Are communication channels functional during this crisis? Market resilience. How do energy prices, supply chains, and utilities react under the crisis? Wargaming is not about predicting the future. It is about preparing systems to remain stable across multiple futures. A major pillar of strategic foresight is anticipating technologies that could reshape the global energy system. Examples include hydrogen supergrids that interconnect continents through pipelines and shipping networks. Another example is that of small modular reactors offering flexible, lower-cost nuclear deployment. Finally, we must recognize that future energy risks extend beyond current governance structures. Institutions such as the IEA, IRENA, and UNDRR are increasingly building foresight capacities. There is still no coherent governance framework for space-based energy systems, protection of subsea cables, and AI-controlled energy networks. This regulatory vacuum creates vulnerabilities. If governance does not evolve as fast as technology and climate risk, the world faces widening exposure to systemic shocks. Let us examine quantum technology and energy security. Here, we move into a frontier area where physics, cyber security, and energy governance collide. Quantum technologies promise extraordinary gains in efficiency and system optimization, but they also introduce risks that traditional regulatory frameworks are not prepared for. Quantum algorithms can optimize grid generations, smooth the integration of intermittent renewables, reduce congestion, and minimize storage requirements. The result is that energy systems become more efficient, cheaper to operate, and more predictable, especially in high renewable scenarios. Let us examine Quantum cybersecurity threats. Quantum computers can break the cryptographic systems that currently secure our digital infrastructure. Protocols like RSA and ECC, which protect banking, defense and grid communication, can be rendered obsolete. For the energy sector, this creates several high-stakes risks. For instance, smart meters, SCADA units, and grid controllers could be hacked if their encryption is broken. Cross-border electricity interconnectors, which rely on encrypted communication, could be disrupted or spoofed. The strategic risk is that state adversaries with quantum capability could paralyze national grids. To manage these risks, energy systems will need a transition toward quantum-safe energy infrastructure. Current mitigation pathways include quantum key distribution, post-quantum cryptography, and quantum secured communication channels. Let us examine space weather and solar storm risk. Here, we look at an often overlooked but extremely powerful force that can disrupt global energy systems. Space weather. While we usually think of energy security in terms of geopolitics or climate risk, the sun itself can alter or trigger catastrophic failures. While we usually think of energy security in terms of geopolitics or climate risk, the sun itself can trigger catastrophic failures. Modern grids, satellites, and digital energy platforms are all vulnerable to intense solar activity. Let's begin with what solar storms actually do. The sun periodically releases solar flares and coronal mass ejections, massive bursts of charged particles. When these particles reach Earth, they disturb geomagnetic field, producing what we call geomagnetic storms. A Carrington type storm, the kind that occurred in 1859, would be devastating today. Modern modeling suggested it would shut down GPS networks, affecting navigation, timing signals, and synchronization of power grids. It can cripple satellite communications, including those used for weather forecasting, telecom, and remote sensing. It can also induce geomagnetically induced currents in high voltage transmission lines, which can burn out large power transformers. Solar storms also affect the parts of the energy system we increasingly rely on. For instance, satellite-based wind and solar forecasting. It becomes inaccurate or unavailable during geomagnetic events. GPS-guided turbine yaw alignment can malfunction, reducing wind farm output. Navigation systems for LNG shipping, which depend on GPS, become unreliable, posing serious safety and logistical challenges. Space-based solar power platforms are highly sensitive to solar radiation surges. These effects reveal a major blind spot. Most global energy systems assume stable satellite services, yet space weather can interrupt them instantly. Let us examine the resilience strategies. Resilience strategies include hardening transformers and grids against geomagnetic induced currents, satellite redundancy programs, and national geomagnetic early warning protocols. These measures mark the beginning of a long-term effort to integrate space weather into mainstream energy planning. Let us conclude our discussion. Energy security in the coming decades is shaped as much by emerging frontiers as by traditional risk. Space-based and offshore energy systems signal a shift toward new resource domains, but they also introduce technological, legal, and geopolitical uncertainties. Climate tipping points underscore how quickly stability can unravel when thresholds are crossed, amplifying systemic shocks to energy infrastructure. Strategic foresight frameworks in turn help anticipate long-range disruptions and map alternative future pathways. Quantum technologies add another layer of complexity, offering transformative capabilities while exposing encryption and grid management systems to new vulnerabilities. Space weather hazards such as solar storms further remind us that energy security is increasingly dependent on planetary scale forces beyond human control. These developments mark a transition into an era where securing energy requires preparedness for non-linear change and resilience across multiple technological and environmental domains. Let's see what's coming up. The upcoming week will explore nuclear energy law in India, examining its regulatory architecture, liability framework, institutional oversight, and the evolving policy landscape shaping the nation's civil nuclear program. Thank you.